So in this video, we're going to talk about other substitution methods. And the first one we're going to talk about will be Bernoulli's equations. So let's look at a differential equation that's a Bernoulli differential equation. If we have something that's written in this format, dy over dx plus p of xy is equal to f of xy to the n, we call that a Bernoulli equation. So the difference between that and the other ones we talked about is really what's on the other side of the equals. So notice we've got that first derivative over here on the left in both cases. We have some function in terms of x times y. And then we have, in a standard linear differential equation, we have that equal to f of xy. With a Bernoulli equation, that's different. We have it equal to f of xy times y to some power. Now, if n is 0 and n is 1, we actually end up with a linear equation. If n is 1 here, then we could just move this guy and combine those terms. If n is 0, then y to the 0 is 1, and it's just f of x on that right-hand side. So in both of those situations, you actually have a first-order linear differential equation. So that's why we say with Bernoulli equations, n can't be 0 and 1. So how do you solve a Bernoulli equation? To solve a Bernoulli equation, we're going to use the substitution u equals y to the 1 minus n. And what that's going to do is reduce this to a linear equation. And then sometimes you'll be able to use separation of variables. Sometimes, more often than not, you'll have to use the process to solve a first-order linear differential equation. So let's look at an example. So if we look at this differential equation, this isn't quite in standard form. The first thing we would want to do is divide everything by x. So we have dy over dx plus 1 over x times y is equal to x times y squared. So we're in standard form because we have a 1 in front of that dy over dx. So notice this is not a linear differential equation. The issue is really this term over here on the right-hand side of the equals. We have y squared over there. But it does fit the format for a Bernoulli equation. So we're going to do a substitution. We're going to let u equal y to the 1 minus n. So in this case, our n is 2. That's the exponent that's on the y. So we're going to have y to the negative 1 there. So I'm going to box in that substitution. So we have a substitution that we're going to use, but we're going to have to substitute in for y and for this dy over dx. So let's do some algebraic manipulations here. So we have u is equal to 1 over y, which means that 1 over u is equal to y. So there's the substitution we need for y. And then if we were to take the derivative of that with respect to x, remember 1 over u is the same thing as u to the negative 1. And when we take the derivative, we're going to have negative u to the negative 2. And we want to show we took the derivative of u with respect to x. So there's our substitution. So now all of this will go into our differential equation up here. So we're going to have negative u to the negative 2 times du over dx plus 1 over x times y, which is 1 over u, is equal to x times our y, which is 1 over u squared. I'm going to simplify. So now we have that. Now, we really need to divide everything by this term. So we can divide by negative u to the negative 2, which is the same thing as multiplying everything by negative u squared. And what that's going to do is put us in standard form so that we have a 1 in front of that du over dx. So when we multiply through, make sure you distribute to all 3 pieces. Okay, now this guy is in proper form because we have a 1 in front of that du over dx, and then we have a function in terms of x times u, and that's equal to another function in terms of x. This is first order linear. So we need to start out by identifying the integrating factor. Our integrating factor is going to be e to the negative 1 over x dx. When we integrate that, we get e to the negative ln of x. So that's e to the ln of 1 over x, which ends up being just 1 over x. And then we're going to multiply through. If we multiply this equation through by 1 over x, we have that. And it's usually easier to think about it in terms of negative exponents instead of fractions. So now we're going to do our rewrite. How can we rewrite this? Well, it's always the integrating factor, which is 1 over x times u. And that's going to be equal to a negative 1. This is where you would want to check. Make sure this step is equivalent to the one you had before. 1 over x is x to the negative 1. If we were to take the derivative of that, that's product rule. First times derivative of the second, plus second times derivative of the first. And do you see how this is equivalent to what we have over here? So we know we have written this correctly. So now we can multiply both sides by dx, and then we can integrate. So when we integrate something we want to take the derivative of, we end up with just what's in the brackets, 1 over x times u. And when we integrate the right-hand side, we're going to have negative x plus c. Multiply both sides by x. We have u is equal to negative x squared plus cx. So now we have that solution written in terms of u, but remember, we need it written in terms of y. So we said up above that y is equal to 1 over u, and that's the same as u is equal to y to the negative 1. So let's make that substitution. And that's the same thing as 1 over y. And then if we solve that for y, there's our general solution to that problem. So let's do another one. We have dy over dx plus xy is equal to x e to the negative x squared times y to the negative 3. So this is written in standard form. We do have a 1 in front of that dy over dx. We have this y term here that has an x, a function of x in terms of x in front of it. And we have everything else on this side. So notice that y to the negative 3, that's your sign that this is Bernoulli. In this case, our n is negative 3. So we're going to do a u substitution. Let's let u equal y to the 1 minus n. So that's going to be y to the 4th. So if u is y to the 4th, then that means u to the 1/4 is equal to y. And if we were to take the derivative of y with respect to x, we're going to have 1/4 u to the negative 3/4. And we took the derivative of u with respect to x. So now we have some substitutions. We have a substitution for y and a substitution for dy over dx. So now let's make those substitutions into our differential equation. So we have dy over dx, which is 1/4 u to the negative 3/4 times du over dx, plus x times y, but y is u to the 1/4. And that's going to be equal to x e to the negative x squared times y to the negative 3. And our y is u to the 1/4. So I'm going to simplify some things. Just simplifying that right-hand side. So now we need to figure out what we're going to multiply by. Well, we need this term to be a 1 times du over dx. So let's multiply by 4 times u to the 3/4. So if we do that, we're going to get du over dx plus 4x times u. And that's equal to 4x e to the negative x squared. And then when we multiply those u's together, we get u to the 0, which is just 1. So once again, this guy's first order linear. And that's typically what happens with these problems. Every now and then you'll get one that's separable, but most of the time, 9 times out of 10, they're going to be first order linear. So to solve, we need to find that integrating factor. So we have e to the integral of 4x dx. That's going to be e to 4x squared over 2, which is 2x squared. Then we're going to multiply through. This one looks like it's going to be terrible, but it's not as bad as it looks. So when we multiply that first order linear equation through, we're going to have that. Now, we're going to simplify that right-hand side, and then we're going to do a rewrite. So then now if we rewrite, remember the rewrite is going to be the integrating factor times u. You always want to check this just to make sure that you're on the right track. So if we were to take the derivative of that, remember that's what the notation means. You want to take the derivative of what's inside of the brackets. That's going to be product rule. It's the first one times the derivative of the second plus second times derivative of the first. The derivative of e to the u is e to the u. Derivative of the exponent is 4x. So we're asking, is that the same thing as what we have in the previous step? And as you can see, it is. So we are in great shape. So now we can multiply both sides by the dx, and then we can integrate. When we integrate something we want to take the derivative of, we're left with what's in the brackets. When we integrate this guy, this is going to be a u substitution. So I'm going to rewrite this. I'm going to do it in a different color. So 4 is the same thing as 2 times 2. So I could think about splitting that 4 apart into 2 times 2. And the reason I would do that, this is a u substitution. If u is x squared, du would be 2x dx. So we have all of du there. So then when we integrate, we're going to have that 2 that's out front. When we integrate e to the u, we get e to the u. And then plus c. So now I like to get u by itself. We can divide everything by the e to the 2x squared. So then our u is going to be 2e to the negative x squared plus c e to the negative 2x squared. Remember, when we combine these, when you divide and you have the same base, you subtract the exponent. So it's x squared minus 2x squared, which is where that negative x squared is coming from. So now we're going to do a substitution. Remember what we said before for u? Going all the way back up to the top. U is equal to y to the 4th. So let's substitute that guy in. So there's our final answer. There's not a lot we can do with this one. Now, why would I not solve this for y? Well, I'm not going to solve this for y because this is just going to get messy. If I tried to do that, I'm going to end up with a plus and minus 4th root of all of that fun stuff. And we're just not going to, we just don't want to do that. So don't do that. It's perfectly fine to leave your answer like that. If you wanted to go a little bit more, you could factor out, let's see, an e to the negative x squared. And that would leave us with a 2 plus c e to the negative x squared. That would be perfectly fine also. So another type of substitution we're going to talk about is where we have a function written in terms of ax plus by plus c. And we could do a substitution just by letting u be that ax plus by plus c. As long as b is not equal to 0, we're going to be able to reduce this to something that's separable. So let's look at an example of that. So we have dy over dx equals 1 plus e to the y minus x plus 5. Let's let u be that y minus x plus 5. So if that's what we're going to choose for u, then the derivative of u with respect to x would be dy over dx minus 1, and then the derivative of 5 is 0. So what do we need substitutions for? Well, we're substituting in for this, and we also need a substitution for this. So we need to tweak this so that we have dy over dx by itself. So to do that, we're going to move that 1 to the other side. So that means du over dx plus 1 is equal to dy over dx. So now I'm going to box in my substitutions, and then we're going to substitute. So we have du over dx plus 1 is equal to 1 plus e to the u. So notice the ones are going to cancel. So we have du is equal to e to the u times dx. Let's divide everything by e to the u. So we have du over e to the u is equal to dx. Now we can rewrite that as e to the negative u. And now we can integrate. When we integrate the left, that's a u substitution. When we integrate the right, it's just going to be x plus c. So now we have the answer written in terms of u. We're going to do a substitution back in. Before we said u was equal to y minus x plus 5. So we're going to substitute that in. I'm just going to clean that up just a little bit. So that would be a negative y plus x minus 5. Or we could say x minus y minus 5. There's not a lot we could do here. So I'm going to leave it in that format. Okay, let's do one more. So we want to integrate this one. Notice this one is an initial value problem. So we're going to let u be 3x plus 2y. So let's take the derivative. So we have du over dx is equal to 3 plus 2 times dy over dx. It's an implicit differentiation there. So we have a substitution for this and this. We need a substitution for that. So that's where we're going to tweak this. Let's solve this for dy over dx. So we have du over dx minus 3 is equal to 2 dy over dx. And if we divide everything by 2, we have 1/2 times du over dx minus 3/2 is equal to dy over dx. So I'm going to box in that substitution and this substitution. So now let's do it. So substituting in for dy over dx. So this is u over u plus 2. So remember the goal is going to be to separate variables here. So let's go through and multiply everything by 2. So we have that. Now let's combine white terms here. We really need to multiply this 3 by u plus 2 over u plus 2 just to get a common denominator. So when we do that, we're going to have 2u plus 3u is 5u plus 6 over u plus 2. So if we multiply both sides by dx and then move that term, we're going to get u plus 2 over 5u plus 6 is equal to dx, separating the variables there. So now we need to integrate. There's our du. We need to integrate both sides of this. Well, the right-hand side's easy. It's just going to be x plus c. But let's deal with that left-hand side. We're going to have to do long division over here. So we have 5u plus 6 going into u plus 2. 5u goes into u 1/5 times, because 1/5 times 5u is a u. 1/5 times 6 is 6/5, and we are subtracting. 2 minus 1/6 is, 2 minus 6/5 is 4/5. So that left-hand side reduces to 1/5 plus 4/5 over 5u plus 6. So when I integrate, I'm going to get 1/5 times u plus 4/5. This is a u substitution. So you could think about pulling that 4/5 out. You're going to have a 5 here and compensate with a 1/5 here. So this is going to be your ln rule. So now let's do our substitution. We said u was equal to 3x plus 2y. So we have 1/5 times 3x plus 2y plus 4/25 times the ln of 5 times 3x plus 2y plus 6 is equal to x plus c. So I'm going to go through and multiply everything by 25 just to get rid of these fractions. 25 times 1/5 is a 5 times 3x plus 2y. This is going to be plus 4 times the ln of 15x plus 10y plus 6 is equal to x plus 25x plus 25 times c, and that's a new constant. I'm going to call it c1. So 15x plus 10y plus 4 ln of 15x plus 10y plus 6 equals 25x plus c1. So there's our general solution. Now let's make our substitutions, because we have an initial condition. Y of -1 is equal to -1. So if we substitute in -1 for x and y, so we're going to have, I'm going to go ahead and just do it, -15x, 15 times a -1 is a -15, 10 times a -1 is a -10, plus 4 ln of -15 minus 10 plus 6. That's got to be equal to -25 plus c1. Take the absolute value of -19. It's going to be 19. And guys, that's why the absolute value is important, because we know we cannot take the ln of a negative number. So we get 4 ln of 19 is our C1. So then our final solution, if I go back over here, is 15x plus 10y plus 4 ln of 15x plus 10y plus 6 is equal to 25x plus 4 ln of 19. And there is our final answer.